Hi students, in this video we're going to be talking about limits at infinity. When we're dealing with functions, when they tend towards infinity or negative infinity, they're going to have certain behaviors. The three behaviors are the limit can be infinite, the limit will be zero, or the limit is going to be a fixed value. And it's going to be based upon what happens with the numerator of a function and the denominator of that function. For our first example, we want to describe the function f of x equals x squared minus 100 divided by 10x plus 3 for very large values of x. So let's look at that graph first. So when we look at the graph, we can see that when x is very large, our function seems like it's going to just keep growing and growing and growing until it gets to positive infinity. Like if we zoom out a ton, you can see that the graph is growing slowly, but it's steadily growing. And as x goes to the left towards negative infinity, our values get smaller and smaller and smaller, but they tend towards negative infinity. But how does the graph, like, is there a way to accurately describe the behavior for the function? So let's find out. So let's consider the value f of 100,000. Now, if I remember from that table, f of 100,000 was 99,999.97. We also want to consider the value f of negative 100,000. And that was, what was that value? F of negative 10,000.3. So negative 10,000.03. So again, it seems like the limit is going to be infinity when x goes towards infinity, and the limit is going to be negative infinity when x goes to negative infinity. Now, say we had to actually prove this analytically. So when x is very large, the negative 100 isn't going to contribute much to the calculation of x squared minus 100. So we can think about this, like think if x was 50, for instance. So 50 squared is equal to 2,500. And so then if we take out 100, we get 2,400. So that's what we get in our numerator. The 100 had almost no effect on the square of the large value. And similarly, in the denominator, if we had 50 still, we'd have 50 times 10, which is 500, and then plus 3. So we get 503. That 3 didn't really add a lot to the denominator. So what's really going on is for large values of x, f of x is going to behave like, so the x squared, again, the negative 100 we don't actually need. It's going to behave like, and we'll give it a subscript, we'll say like f1 of x or something, is going to behave like just x squared divided by 10x, which of course we can divide 1x away and get x divided by 10. Well, see, now that kind of makes sense, because if we substitute in 100,000 to this other function, if we had f1 of 100,000, well, that's just 100,000 divided by 10, which is 10,000. Look how close that value is to what the actual f of x function spits out. And something similar for negative 100,000. We just get negative 10,000, which is astonishingly close to negative 10,000.03. So what we could say is the limit as x approaches infinity for just regular f of x, this f of x is equal to infinity. And the limit as x approaches negative infinity for f of x is negative infinity. But we can base that on what's happening here. If you substitute in a very large positive value and divide it by 10, you're going to get a large positive value. if we take a very large negative value and divide it by 10, we're going to get a large negative value. So it's simpler to use this reduced function to describe the behavior. And so we saw that that graph behaved like a linear function for very large values of x. That's because x divided by 10 is a linear function. For our next example, we have this function f of x equals x minus 1 divided by x squared plus 1. And we want to see what happens for very large values of x. So again, we're going to hop back over to Desmos. So we'll turn off this function and turn on x squared minus 1 divided by x squared plus 1. So if we zoom in, now the graph behaves kind of weirdly until we get to about 10. And we can see that the graph basically goes to 0 very quickly. So if we look at our table, we see that, I'm turn on these points, that for large values of x, we end up with a value that's almost 0. If you don't know what these exponents mean, like the 9.9999 times 10 to the negative 7, it means that we're going to have 6 zeros and then a 9. So it's just an astonishingly small value that's approximately 0. Here, so if we had to describe this, it's going to be similar to what we had for the last function. So for large values of x. So again, the term of highest degree is going to be the only one that matters. So for large values of x, f of x will behave like, we're going to give it a new function. So we'll say like f1 of x is, so in the numerator, only the x is going to contribute when x is very large. And in the denominator, only the x squared is going to contribute when x is very large. So this is going to simplify to just be 1 over x. So imagine that you had one cookie or one pizza and you try to give it to one person. Then one person gets one piece, like the whole pizza. If x was 2, we're dividing that one pizza among 2 people. Each person gets a half of the pizza. So if we did this out to like 1 billion, every person would get 1 billionth of that pizza. And effectively, nobody's getting anything because we're taking one thing and dividing it by a very large amount. So what we can see is the limit as x approaches infinity for f1 of x is going to equal 0. And that's also going to be true when this function approaches, we don't need the f1 of x. This is just f of x, my apologies. And this is also going to be true for f of x. Both of those limits are 0 because what we have is a fixed quantity divided by an increasingly large value. And so again, if we look at that graph, it's going to tend toward 0 in both directions. So it's almost on the x-axis, which is y equals 0, our output value. So take note here, in this case, the degree of the, we'll just abbreviate denominator, was greater than the degree of the numerator. And that led to a limit of 0. In the previous example, it led to the limit being infinity or negative infinity, depending upon the signs after simplifying. And for this last one, we're going to describe the function 2x minus 7 divided by 4x plus 1 for large values of x. So if we hop back over to Desmos once more and turn on this function. So again, like initially kind of behaves like a hyperbola. Oh, turn on one more thing. Turn on this asymptote y equals a half. So when x is very large, at some point our values kind of stabilize. They get really, really close to this horizontal asymptote of a half, but it never ever really gets there. So if we look at our table and see what's happening for really large values of x, so look, x is 1 million here, and we get 0.4999, which rounds up to be 0.5. So for this, for large values of x, f of x behaves like, we'll say f1 of x equals 2x divided by 4x. Well, they both have an x in common, so that's the same as 2 over 4, which simplifies to be 1/2. So for really large values of x, our limit is going to be 1/2. And notice that the degree of the numerator equals the degree of the denominator. So when the degree of the denominator equals the degree of the numerator, we get the implication here is the limit is the ratio of the leading coefficients. And we'll abbreviate coefficients, long enough word. And the leading coefficients are 2 and 4. So a special thing happens when the degree of the numerator is exactly 1 greater than the degree of the denominator. We get a slant asymptote. To find a slant asymptote, we do polynomial long division, and we'll see what we get. And that's what happened in that very first example, by the way. So let's see. So we see that the degree here is 3 and the degree is 2. So we know that the limit is going to be infinity and negative infinity in some order when x goes to positive or negative infinity. But we can also like just generally predict what the values are going to be if it's linear. So let's see. We're going to take this function x squared minus 1 and divide it into x cubed plus 0x squared minus x plus 1 and see what we get. So x squared divides into x cubed. X times x squared is x cubed. X times negative 1 is negative x. Remember, for a long division, we switch the signs and we add. So that's going to be 0, 0x squared, and we're going to get 1. So and then we get the plus 1. So we stop when this x squared minus 1 is going to be larger than the value of 1 for really large values of x. So this is the same as having x plus then 1 over x squared minus 1. So this part is going to tend to 0 when x is large, when x goes to infinity. So f of x equals x cubed minus x plus 1 divided by x squared minus 1 behaves like y equals x for large values of x. But we already know that, because another way of doing this is just taking the ratio of those two things. All right, so now some quick examples. Is this the last one? Yep, the last one. So we want to examine the limit when x approaches infinity of that thing. So we're going to say this is approximately the limit when x approaches infinity of the cube root of x to the 6th divided by 4x squared plus the square root of 3x to the 4th. And that is exactly equal to the limit when x approaches infinity. So the cube root of x to the 6th is x squared. And then this is going to give us 4x squared plus the square root of 3, x squared. And so then we can take out an x squared. So we end up with the limit as x approaches infinity of x squared divided by x squared times 4 plus the square root of 3. So since those cancel, this is 1 over 4 plus the square root of 3. So for large values of x, our y values are going to approach that particular value. All right, that concludes our video on limits at infinity. So let's recap what we've what we talked about quickly. So here, for our first point, this is going to be when the degree of the numerator is greater than the degree of the denominator. For our second example, let's zoom in. It's going to the limit is going to be 0 when the degree of the denominator is greater than the degree of the numerator, and equal to some number is when the degree of the numerator equals the degree of the denominator. All right. Of course, we'll do a lot of practice in class. See you all in class.